Hello and welcome to a video about a worked out problem that I'm going to use MATLAB to solve from chapter 2. It's going to be a piston and cylinder problem, and you're going to have your share of piston and cylinder analysis problems in thermodynamics class. So I thought I would sort of give you a demo of how could you solve this basic type of a problem in MATLAB, since you've already taken and succeeded in a MATLAB course. So let's get started. And I'm a little rusty, so I'm going to share my screen and here we go. So I've got to move my Zoom menu. Okay, I think we're good now. So this is going to be problem 254 from the textbook. And this is a homework that's been assigned in one of the sections here in spring semester 2025. Well, let's look real quickly at what are the basic ideas for solving a thermo problem in the first place. I hope this slide looks familiar to you. And here's my basic recipe that I use when I'm solving engineering problems in general. First, just read the problem in words. What's the objective? The second thing I do is nearly always start with a sketch, and that's where I put down given information, but it helps me to visualize with some type of sketch, even though one is provided, might be provided in the problem statement. I still draw a sketch in my own pencil and paper. Then I plan my work. What am I going to do? What's my path forward for solving? And then finally work through the solution. And that's where MATLAB comes in, right? And so we don't just read the problem and go right to MATLAB. In the same way, we don't just read the problem and go to our calculators. We need to do some pre-work before we start working through the solution. We'll work down the page. We need to write down fundamental equations that we will use, do the best to show and explain our work. Keep in mind that units are just as important as values, and we're going to try to explain the work as we go along. Okay, so here's the problem. I'll read it to you and hopefully you can read along. So it's problem 254. A sketch is shown. A gas is contained inside a piston and cylinder assembly. A vertical shaft with a cross-sectional area of 0.8 square centimeters is attached to the top of the piston. And based on the sketch, I see a force pushing down on it. The total mass of the piston and shaft is 25 kilograms. So that's the mass of the piston and shaft. While the gas is slowly heated, the internal energy, so we're adding heat to the gas inside the piston and cylinder. Gas is slowly heated. The internal energy of the gas increases by 0.1 kilojoules. That's going to be a key. The potential energy of the piston and shaft combination increases by 0.2 kilojoules. That's going to be a key. And it also says that a force of 1,334 newtons is exerted downward on the shaft, and that would be in addition to the weight, as shown in the figure. The piston and the cylinder are poor conductors of heat, and friction between the piston and cylinder is negligible. The local atmospheric pressure is 1 bar. That would be 100 kPa. G is 9.81 meters per second squared. And so here's what you're asked to find. A, the work done by the shaft, that the 1,334 newtons pushing down as shown in the sketch. B, the work done in displacing the atmosphere. The piston's going to move, and that must mean that work is being done on the atmosphere. C, the heat transfer added, the heat added to the gas. And then D, it says, using the calculated and given data, develop a detailed accounting of the heat transfer of energy to the gas. And so that's going to be much more of just a summary of all of the numbers that you have gotten in solving the problem. That'll be the accounting and sort of adding up. Do all the numbers add up? Okay, so let's get started. We're not going to go right to MATLAB. We've got to figure out what we're going to do. And so if you're doing this yourself, you'd probably be doing this on pencil and paper. Oh, you might be doing it with a tablet or something like that, but you're going to be writing and sketching, I hope. And so we've got to start with an equipment sketch. And then when we study this given equipment sketch, we realize we'd better draw a free body diagram of the piston alone. And that's what's going to teach us. It's going to show us how do we figure out the pressure of the gas inside the piston and cylinder. So here's our free body diagram. Let's look at the downward forces on our sketch. I can visualize the surroundings, the atmosphere pushing down on the area of the piston. That's one force. Another force clearly is 1,334 newtons. That's clear, 1.334 kilonewtons. Okay. And then where would the last force pushing down be? Well, we're given the mass of the piston and shaft, and so that was given. And so there's going to be the weight of the piston in addition to that 1,334 newtons pushing down as well. So we've got three downward forces. What's pushing up on the piston? Only one upward force, and that upward force is going to be the pressure of the gas times A of the piston. Okay, so that's going to be a good learning. Also, do you remember in the problem it said heat is added very slowly? So there's no acceleration of the piston, things are going slow. And so that must mean that at all time during the process, the sum of the downward forces is going to have to exactly equal the sum of the upward forces. So the sum of these three forces is going to have to exactly equal this single upward force. And so do you see that gives us clearly, now we can see, I think I see how I will calculate the pressure of the gas. And another thing to see is that the pressure of the gas is going to stay constant because all of this given information, it's all constant. So the pressure of the gas is going to stay constant. Okay, so let's see. Looks like I've covered a lot of things. Let's plan our work. So we've studied the free body diagram. Okay, so first bullet item, okay, check. All the downward forces are constant. Okay, we can determine the pressure of the gas using the free body diagram. Okay, so that gives us the pressure. But then now what? We've still got to figure out work terms and things like that. And you can do some head scratching and think about your keys and how will you approach it. And one thing that smacked me in the face was something given. It said potential energy increases by 0.2. And that tells me potential energy. That must mean that the piston is rising and it's a given amount of energy in kilojoules. And so let's see, I remember from the textbook reading that potential energy change is going to be something like a force through a certain vertical rise. And so I'm going to suggest that given this information, we can calculate delta Y, the amount of position, the amount of distance that the piston rises. We can calculate delta Y. Okay, so more head scratching. Wow. If you've got delta Y and you know the diameter of the piston, you can calculate the area of the piston easily. And so then delta V, the change in volume of the gas, is easy. That's going to be area of the piston times delta Y. Easy. Okay. Well, gosh. So that's going to help us along the way, because then do you see that, remember from your reading, for a gas in a closed system undergoing a quasi-equilibrium process, that let's see, the work is integral PdV, and we just showed that the pressure is constant. So if we can draw a pressure volume diagram, we've got an easy integral to calculate, easy integral to evaluate. P constant times dV, that's delta V. So the work done by the gas, the entire work done by the gas, is going to be P, the pressure of the gas, times delta V of the gas. Okay, so that's going to be pretty easy. We still got a few things to do. Okay, it's in the assignment. It said determine the work done on the surroundings. Okay, for this particular calculation, we've got to change our thinking and think about the surroundings as a closed system. And let's see, let's use some common sense 101. And if the if the piston cylinder gas changes its volume by a certain amount, doesn't it make sense that the surroundings would change its volume by that same certain amount, except in the negative? So the surroundings would kind of decrease a huge volume by a little amount, by the little amount that the gas increases. So I could argue that the work done by the surroundings, in other words, the work out by the surroundings, is going to equal P of the surroundings times delta V of the surroundings, which will be a negative number. And so we're going to get a negative number for the work done by the surroundings, or in other words, the work done by the gas on the surroundings. So that's going to be the key for that. And then let's see, we were also asked for what's the heat transfer into the gas. Well, if you don't know where to start with that, and you're just starting solving these problems, a good tip is, if you don't know where to start, write down the first law, and the chances are good the first law is going to help you out. So let's write down the first law. We haven't even started with MATLAB yet, have we? But we're just trying to figure out what we're going to do in MATLAB. All right, Q in, that's what we're looking for, minus W out. We just found it. Delta U of the system, a given number. The change in potential energy of the closed system, not the piston, but the closed system, that's 0. Okay. And the change in kinetic energy of the closed system, that's also 0. The piston's not moving anywhere. It's sitting on the table or on a hot plate. Okay. So you see that we're going to end up with one equation and one unknown to find the heat transfer. And then the accounting, we're just going to write down the things we found. Okay. So if we're not interacting, there's nobody on the call here in Zoom, but you might say, well, it said in the problem the potential energy changes, and it did, but it's the potential energy of the piston, and that metal piston is not part of our closed system. So that's a key thing to recognize. That's delta PE, that's the potential energy of the gas contained in the piston cylinder, and it's not really changing. Okay. So here's what we're going to do in MATLAB. This is the sequence that we're going to do our solution in MATLAB. First, we're going to determine the pressure of the system. Then we're going to determine the change in height of the piston to that potential energy change, and we'll determine the volume change. We will then determine, we're going to use work equals integral PdV of the gas to determine all the work that is done by the gas in the piston and cylinder. Work equals integral PdV. Then we're going to go and we're going to move to part C, determine the heat transfer using the first law. Then we're going to do calculate the work done by the system on the shaft, right? So a force through a distance. So this is just kind of like a little side job. Force through distance, we know that the force is constant, that was given, and delta Y we have solved up here. So that'll be the work done by the shaft. It's going to be a negative number. It's going to be the work done on the shaft. Part B, the work done by the system on the surroundings. It's going to be a negative number. And so remember, if the volume change of the surroundings is going to change just a little bit by the exact amount of the volume increase of the piston and cylinder. And then finally, part D, we're going to have a little accounting problem, which will be mostly tabulation. Okay, so I'm not going to force you to sit here on a video and watch me code out everything in MATLAB. So we're going to go live here, and you're going to see this as my MATLAB file. So I have created the MATLAB file. But let me give you an overview of what you're going to see. Early on, you're going to see some given information. Okay. you're going to see sort of an outline of what we're going to do in the MATLAB solution, and then we're going to solve the problem. And I'm going to try to point out some things as we go live. So let me see if I can pull that off. I'm going to escape out of PowerPoint, minimize it, and then I'm going to bring up my MATLAB. Okay, I think I'm ready to go. And I've loaded in this file that's called prob02x54.m. Okay, and let's just quickly see how big it is before I give you a little tour of it. Okay, it is 116 lines long. Okay, so notice what I'm doing. I'm starting it. So here I'm starting out with all of these comments, these percent signs. They're all comments. I'm typing out things and sort of, and do you see that I use these little dashes and a comment as sort of a dividing, a visual division of topics. All right, so I've put in all of my given information. I've typed it in comments as best I can. The next thing I did was I typed out in comments the approach. So I've got some stuff written down on pencil and paper, and I've kind of I've taken a little time, a few minutes. It's not immediate, a few minutes to type out in general what I'm going to do with the solution. Okay, and now I'm going to begin my MATLAB solution. But I hope that you see that. Let me go back up. I hope you see that it's documentation, because if you're anything like me, you'll come up with a nice solution like this, but in a few weeks, you're sort of going to forget what you did. And since I can't include a sketch, no handwritten notes in MATLAB, this is the best I can come up with. All right, so solution. Well, okay, here we go. And so finally, I'm done with some comments, okay? But notice what I'm doing is, so I'm entering my given information, but and I'm well, for example, atmospheric pressure. Do you see I've selected a variable name, PATM? Kind of makes sense. Area of the shaft, 0.8 times times 10 to the minus fourth square meters. The force of the shaft. You see that I've put in 1.334 kilonewtons instead of newtons, because I'm planning ahead in my solution. I'm planning ahead. I'm thinking ahead with units, and I'm going to be working in pressures of kPa, kilonewtons per square meter. Areas are going to be square meters. So I'm just I'm looking ahead and say, I might as well just express my constant, the given F shaft, as 1.3 kilonewtons instead of 1,334 newtons. Now, another thing to point out in my work, here's my little semicolons. In other words, I'm suppressing the output of these entries, suppressing that to the command window. You'll never see these in the command window. I'll show that in a minute. Okay, so there's my semicolons, and then followed by a comment, a percent sign. And do you see that in my work, I'm very careful. Instead of just saying PATM equals 100, I'm including units, and I'm trying to do that throughout all of my data entry, all my given information data entry, in addition to putting in numbers with some common sense variable names. Delta PE, delta U, change in internal energy, kind of makes sense. You get to select all these things. You're programming. But don't forget in comments to say what you're doing along with units. Now, all right. So the next thing I'm doing is planning. I'm planning for the results. And so I came up with a title the command window output. I've got nothing over here to start with. Okay. So I'm just going to start displaying result for problem 2 x54. Okay, with some dashes to be making an underline. So this DISP is really handy for me. Okay. Display the weight of the piston. Well, that was given, but I think it's valuable to go ahead and write that out. So you see here, see how I'm kind of explaining my work as I'm working down the screen or the page. Display the weight of the piston. I'm just saying result. That's just some dummy variable name. Text, W piston equals, and then number to string WP, that's the weight of the piston. In other words, change a number, WP, into a string so you can print it out, okay? And then with finally, in little quotes, kilonewtons, that's going to be my unit. So that's just displaying to the output. Okay, finally, we're getting to some math. I'm calculating my piston cross-sectional area. Area of the piston is pi over 4d of the piston squared. You got it, okay? And you see how I'm continuing suppressing my output until I choose to write something to the command window. I'm writing out A of the piston, number to string, square meters, okay? But I'm continuing to say what I'm doing and including units as I'm going down the page, even in MATLAB. The atmospheric force pushing down, P atmospheric times A of the piston. Okay, now I'm up to the point. I've got all my downward forces. Did I get the weight of the piston? Oh, there it is. Sure, there it is. The weight of the piston is the mass of the piston times G. You see how handy that is to be able to review your work. I'm showing, oh, and I calculated in newtons first, and then I divided it by 1,000 to get it to kilonewtons. Okay, WP, that's my variable name, weight of the piston. All right, so let's see, where was I? Gosh, close. So I've got all my downward forces. There they are, WP plus the force of the shaft, the force of the atmosphere pushing down, 3 forces pushing down. That's the downward force, must equal that. And so P of the system must equal the downward force divided by A of the piston. So I'm getting P of the system, P of the system. All right. And then I'm going to display the resulting pressure. Next, determine the change in piston position using that concept of change in potential energy. So here we go. Delta Y equals change in potential energy, delta PE, over the weight of the piston. And I'm checking through all my units. I might go off to the side for some pencil and paper to check my units. And I'm going to verify that it is in meters, okay? And then I will, just to check my work, I'm going to write that out to the command window. What's next? Next is determining the change in the volume, delta V. See how I'm writing that out? And I'm skipping a couple of lines. I'm describing what I'm doing as I'm working down the page in comments, all right? Delta V, change in volume, is the change in position, delta Y times A of the piston. That's easy to understand. Write it out to the command window. The work done by the system, work equals integral PdV. And I've shown back on pencil and paper in my sketch that the work out is, it's a constant pressure, so it's P system times delta V. And the units will be, well, kilonewton meters. We've got kPa times kilonewtons per square meter times cubic meters. That's going to be kilonewton meters or kilojoules. Display the work done. Okay, next. We're going to write out the first law. And I wrote the first law out. I wrote out the first law in a comment, but then here's the math. I'll solve for Qn. Solve for Qn equals delta U plus W out, which we just calculated, W out of the system. And so we've got a number for it, and I'm going to display it to the command window. Now we're going to work on, let's see, part A, the work done on the shaft. The work of the shaft, W shaft, equals the force of the shaft, a constant, times delta Y, force through a distance. I've got a number. It's going to be kilonewton meters. Okay, because remember, I entered F shaft as kilonewtons. All right, and so output, work done on the shaft, is some number. Work done on the surroundings. So we showed with pencil and paper that the work done on the surroundings is the atmospheric pressure times the change in volume of the atmosphere. Change in volume of the surroundings, which is just delta V. Okay, so the work done on the surroundings is that amount, and it should be well, let's see, let's just say that that's the work done on the surroundings. So I'm writing that out in text. Work done on surroundings equals that number. Okay, so that's all of our, basically our calculations. How would we finish our assignment, part D, summarize the heat transfer accounting? Here's what you notice how in this section, it's mostly displays, DISP. So I've tried to figure out how would I display things well and how would I check my work. The first thing I'll do is display the heat in, Q in. I'll display that, and then I will dutifully tabulate to the command window increase in internal energy, the increase in piston potential energy, the work done on the shaft, the work done on the surroundings, and that's going to take care of all the little parts. And then one last, I'm going to check my work. So I'm just going to create a variable called check. Check equals delta U plus delta PE plus the work done on the shaft plus the work done on the surroundings. And then I'm going to report the value of check. And then with my eyes, I will see if the heat transfer in equals the check value. Okay, well, I might have taken a lot of time explaining things to you, but it took a little longer to do this mechanically on my keyboard. But let's run. Let's see what happens when I click run. I'm going to run my MATLAB program. Woo! It ran. Thank goodness. All right. Well, let's see what I got over here. Here's my text, result for problem 254, a nice little line, okay? The weight of the piston, the area of the piston, okay, weight of the piston in kilonewtons, okay? So remember, this is all work that was pre-work needed before doing parts A, B, C, D. Okay, I calculated the work out, 1.9 kilojoules. That's the work out of the gas in the piston and cylinder. That's the total amount of work out. It went to different places, didn't it? It went to doing work on the surroundings. It went to doing work on the shaft. And it also went to raising the potential energy of the piston, all right? QN, I found a number for that, okay? MATLAB found it for me, 2.02 kilojoules. And then also that side work done on the shaft is 1.09 kilojoules. Work done on the surroundings, 0.64 kilojoules. And then finally, the accounting. So I repeated my heat transfer in, 2.0284 QN. I skipped a line just to try to make visually nice, okay? Here's our increase in internal energy. That was a given number, wasn't it? Increase in potential PE, that was a given number. The work done moving the shaft, we calculated that. The work done on the surroundings, we calculated that. And let's add up these four numbers. They add up to 2.0284. And we'll check with our eyes. UN 2.0284. Yay. So this is the MATLAB solution to a homework problem. Let's see. Oh, I keep sharing. I'm going to minimize MATLAB now. I'm going to go back to PowerPoint from current slide. Okay, here we are back again in PowerPoint. I tried to give you a tour of that MATLAB file that I'd already created, okay? So remember, I start out with basically typing out given information in comments so that I can use words to say what I've got. Then I created sort of another little block that's the basic work outline of what am I going to show in MATLAB. Then I started my work, and please do see, I'm trying to showcase what's a way to solve thermo problems in MATLAB. I created logical variable names, just use a little common sense 101. When I was an undergraduate when I started programming, my variables were A equals 100, B equals 0.1, C equals 0.8, E minus 4. That was the way I was thinking, like out of math. And boy, that didn't work out so good for me, because once I created the program and set it aside for 2 weeks, hell, I couldn't remember what's A, what's B, what's C. And I also did not use comments hardly at all when I started programming. So I've learned some tough lessons as the years have gone by. Okay, units. So in MATLAB, notice here I'm suppressing the numerical output of these MATLAB entries. I'm adding comments that includes units and the English word names of these variables. Okay. And I'm titled the command window output. I'm doing that here and then continuing to work down. Okay, so that's kind of a key to point out, I think, is suppressing data entry that's going to be ugly in the command window and adding comments explaining what are the variables and what are the units. Okay, so notice here in my, as I'm solving the problem, do you see that I try to spread my work out? I try to use dashes and comments to kind of separate the work I'm doing to make it visually easy, both for myself when I'm troubleshooting. This thing didn't run the first time. So I had some errors here and there. Okay, it helps me troubleshoot my own work, but it also helps others who are looking at your work, maybe evaluating how you're doing. It helps them see that you're doing a great job in explaining your work as you go. Comment, solution, steps. That's a key. Okay, and so then continue to comment solution steps. Once we got down to the accounting, then you see that I'm trying to explain the different things that we're doing. And look, on this one, gosh, oh, no, that's right. This is still continue. I'm sorry. This is still continuing the solution. And then finally, the accounting. Okay. Nearly no math in this accounting section. The only math that I did in MATLAB was to create that dummy variable called check, where I added the different numerical values up to check against the heat transfer in. And so this is the way I created my accounting, so it would be pretty going out to the command window. Okay, and then here's the screenshot of the command window. This is just for you to consider adopting as you're solving MATLAB problems. There's a title, sort of an underline with dashes, some intermediate values. That helped me troubleshoot my own homework by calculating, having intermediate values. Did they make sense? The key values that were asked for. Finally, down here, the heat transfer accounting that were also asked for. And also recognize here, I'm including units in my command window output. I'm always including units with my numbers. And that's why I suppress numerical inputs, and then I format the inputs and the calculations to be able to include units in the command window output. That's a key. Okay, you say, well, that's pretty cool, but I'd kind of like to see what this guy did. Would he share this with us? And the answer is yes. I would be delighted to share this MATLAB program with you. Now, you don't want to just turn this program in and represent it as your work, do you? That would be a violation of the honor code. And in fact, so let me show you how to possess this file. Let me get out of PowerPoint. Okay, I'm out of PowerPoint, minimizing that. And I'm going to go to my Canvas site. Here I am on my browser in my J's Toolbox Canvas site. And this is the tutoring folder. And notice here, a lot of times you folks are going to be clicking on homework problems. I've stored this MATLAB file in my MATLAB folder. Let's click on the MATLAB folder. And at least today, there's only 3 files in the MATLAB folder, and here it is. So let's click on, so you can possess this by simply clicking on the file. It's going to come up in your Canvas browser, and then all you got to do is download it, right? So in order to possess this file, prob010X54.m, simply click download up here, and it's yours, just like that. So encourage you to download it, have a look at it, see what I did. What did you like? What did you not like? Is there some practices that you'd like to adopt or ignore? Or you might have some better ideas on how to create a great looking and effective MATLAB program that can solve problems. Okay, so back to PowerPoint. Okay, I showed you how to download the file, um, develop your own MATLAB problem-solving style. So this is not the style, it's simply a suggestion. And I do want to point out some advantages and disadvantages of using MATLAB to solve thermodynamics problems. So what are the advantages? The advantages are it forces you to go through a disciplined solution because you're programming. Okay. You're going to plan your work, but in the program, you've got to be disciplined or it's not going to run. So, okay. A lot of times you're going to find in thermo that you've got repetitive assignments. Homework problems they're not totally repetitions, but they can be very similar. And so doing code in MATLAB can speed solution time when you have problems that look a lot like previous problems. You're not starting from scratch, pencil and paper and calculator every single time. You can leverage previous work using save as. Okay. Now, looking ahead towards your working world, once you get your degree and you go out and you are in the working world, you're going to find that a lot of times you have very similar problems over and over and over again. And this way, if you use MATLAB as you're working, you can come up with lots of great solution templates to speed your effectiveness at work. In other words, things that have been very similar that you're doing over and over again. This can give you a library of solution templates to go from. Okay, so those are the advantages. Oh, and something I forgot. I got to come down here at the bottom of the slide. If you're going to try to solve homework problems with MATLAB, what are you going to need to turn in? And I should say something. There's a number of things you must turn in. Don't just turn in MATLAB code. That will be useless to your instructor or the person grading your work. Just turning in MATLAB code, nobody is going to try to troubleshoot or study your MATLAB code. Certainly you're going to want to you will want to turn in your code to demonstrate that you're turning in a command window output that you've created. You're not copying from somebody else. So command window output, definitely you want to turn in. But most important, a good solid solution includes a sketch. It includes a plan for solution. So I don't have immediate suggestions for you, but you have to recognize that a complete engineering solution that you would turn in for a grade on homework would be some type of document where you've started with a sketch and outlined your pre-work, maybe pencil and paper, scanned in, or an image of your personal work, somehow a MATLAB code, maybe it's a screenshot, okay, and then command window output, which would certainly be some type of screenshot. I don't have any recommendations of how you would bundle that together, but that's a little bit of a disadvantage, isn't it? So, here's my disadvantage: awkward for single document solution. Awkward for single document solution. That would be tough, but I do want to stress you don't just turn in MATLAB code as here's my solution to the problem. That nix on that. Okay. Here's another disadvantage is that the work that you'd go through to create solutions in MATLAB, creating a program, that is a different sort of skill set than what you're going to be doing on your quiz and test. I'll be quite surprised if any instructor says, oh yeah, if you want to sit down there with your PC and create solutions in MATLAB for a test or quiz situation, very surprised if that moves forward anytime soon. I can visualize that in the future, but not now. So anyway, do recognize that this might be perhaps going the extra mile for students who you've finished a solution using a calculator, pencil and paper. You're training yourself to do well on quizzes and tests, and then maybe undertake go the extra mile and see how you might solve this in MATLAB. Now, more complex problems in this class, you're going to find that you can save a lot of time working in MATLAB for a number of our complex system analysis problems, but that's all for another day. And so this, I'm going to advance. No, this is my last slide. And so let me just leave you with that. I wanted to illustrate to you how would you solve a basic, not simple, but a basic problem, piston and cylinder problem in MATLAB. How would you solve that? And so think about maybe using MATLAB for problem solving in this course, maybe in some other courses that's not your MATLAB course, as you go along. I'm learning this is a very powerful tool. Although I am an experienced programmer, I began learning program in 1972. I started learning programming in 1972. I used programming a lot in my engineering practice world for about 35 years. A lot of programming, but not in MATLAB. So I've only been using MATLAB for about 3 months now. But having that programming experience has really helped me get up to speed in MATLAB. Tremendous problem-solving tool, tremendous tool for thermal systems analysis as well that I'm now discovering. So I'm going to leave it there. And if I can figure out how to stop recording, I'm going to be in good shape. Yes, so when I quit sharing screen, my stop recording button appears. So here we go. I'm going to stop recording. Wish you all the best for success in your class, and think about using MATLAB to start solving engineering problems.